Good morning. So we have completed alkanes in the hydrocarbon section. Today we are starting with alkenes. Alkenes and alkynes to certain extent behave same, but alkenes in itself covers vast mechanisms which otherwise are also very important to understand. And the most important is to apply when the question appears which type of mechanism is operating, what should be the major and the minor products. So, our today target is to start the preparation of alkanes. For that, we are assigned two lectures, that is today's and tomorrow. And in the coming weeks, we'll go for properties of alkenes. Okay, so let's start with preparation of alkenes. Now, as far as preparation of alkenes are concerned, if we could say there are certain basic mechanisms that we'll go through. But first of all, what could be the general formula of alkenes? If I compare with respect to their saturated corresponding molecules having same number of carbons, that is alkanes. So with respect to them, alkenes will have two hydrogen less. Their general formula is CnH2n. As we have told that alkanes are called paraffins, on the same line, alkenes are called olefins. Olefins used to mean that something which is oil forming. Now, how this name came that it is oil forming, initially, very old, in a very old timing in history, it was found that the halogenated product, the halogen added product to alkenes, were having an oily appearance. Due to that oily appearance, they were said to have a oil forming tendency and were named olefins. Now, alkenes and alkynes are unsaturated compound. What are unsaturated compound? Unsaturated compounds are those which have C double bond C or C triple bond C in them. Now, please remember that for unsaturated compounds, they should not be aromatic. Aromatic compounds are having C double bond C and C triple bond C sometimes, but they are not called unsaturated compounds. So, after identifying that yes, a given molecule has C double bond C or a triple bond C or both, the next step is whether it could give electrophilic addition reactions or not. To confirm that a given compound is unsaturated, besides this condition, it should also be capable of giving spontaneous or preferred reactions as electrophilic addition reactions. In case of aromatic compounds like benzene, it is not called unsaturated because it does not give addition reactions like bromine water decolorization or Bayer's reagent decolorization or conversion to brown PPT, etc. Okay, so they are for today. I can say that alkenes are definitely unsaturated compounds. Now, let us have a look at the methods of preparation of alkenes. If I could classify very broadly, alkenes, alkenes can be prepared mainly by three methods. Now, what are these three methods? A very broad classification, I would say. They can be prepared by three methods, a very general class of reaction called elimination reactions. Second, you can prepare them by partial hydrogenation. Partial hydrogenation of alkynes, that is, we would only hydrogenate one pi bond of alkynes and the other remaining as such. Writing a wiggly bond, this type wavy bond is called wiggly bond, indicates that this H could be cis or trans. Both configurations are allowed. So it is cis or trans. So partial hydrogenation of alkynes will also lead to the formation of alkenes. Third method of preparation which could be there is a Wittig reaction method. It is a characteristic reaction for for aldehyde ketones, and is an example of a different mechanism called as an AE. Okay, so first let us proceed for elimination reactions. Today we are going to concentrate on elimination reactions only. Now, point number one, what is an elimination reaction? To classify it as a very general class, I would say if due to any reagent or a physical conditions that we have created, whatever the reason may be, if we eliminate this A and B, what all methods we'll discuss a little later, but if we eliminate these A and B, then this is an example or a basic example of elimination reaction. Now, elimination reaction, the conditions in which they are eliminated on the relative positions of the groups that we are going to eliminate have been classified into different categories. Let me help you to go through some classifications. Say first, classification first we are having based on the relative position of the leaving groups. Based on the relative position of the leaving groups, whatever we are eliminating, उनका relative position क्या है? Relative word I am using because I cannot use the term IUPAC here. IUPAC may be different. IUPAC is based on lowest locant rule. So please keep in mind we are talking about the relative position of the groups that we are eliminating from the substrate. First, I am saying beta elimination. Now, what is beta elimination? If we are eliminating certain groups which are relatively placed 1 and 2 or are relatively placed at adjacent carbons, or I can say besides first group the other is placed at the beta carbon with reference to one eliminating group, then it is known as beta elimination. And in fact, as far as our syllabus is concerned, we will be going through this type of elimination as maximum number of reactions will be following this. This is the most important one. I cannot say that others will not come across. We will. But the 90% of the questions that are relevant for JEE, mains, advanced, and NEET are from beta elimination. So we eliminate A and B. Now, when we eliminate A and B, certainly a question may come to your mind that what is the mode with which these A and B are eliminated? Will they be eliminated as some charged bodies? Will they be eliminated as some free radical? Will they be eliminated by some pericyclic cyclic mechanism? Certainly, these questions are very justified, and I'd like to address them in coming part of my lecture. So just an introduction, what is a beta elimination? When the two groups that we are removing from the substrate are placed at adjacent carbons, then it is known as beta elimination. You are very well versed with this type of elimination, I can say, because in NCRT you might have come across this as the most common. Let me exemplify: dehydration of alcohol. When you do dehydration of alcohol with concentrated H2SO4 heat, then from one center I am losing OH, from the other I am losing H. So overall as a whole, I am removing the groups from this relative position 1 and 2 or alpha and beta, and therefore this formation of alkene falls under the category of beta elimination. The other one, let me right, is again an example where you remove H from one side, X from another by the use of some strong base. I'm not talking much detail here. I'm just taking a net reaction. So don't worry, it should be syn, nt, whatever I written, we'll take care. So when you eliminate this with the help of some strong base, again, an example of beta elimination. As I am not writing it as a salt at this point of time, I'm just eliminating HX. Certainly, later stages will be more clear how to write that HX. Moving to next, if I eliminate two halogens like this. Now, for this elimination, we would be taking help of some metal. You can have sodium, you can have magnesium, you can use zinc, etc. These different type of metals, if we use and we eliminate this halogen dehalogenation reaction, it is another example of beta elimination. Okay, now what is alpha elimination? So we have done beta elimination, and as I told, today's topic will be more concentrated on beta elimination because that is how you are introducing a pi bond, that is how we are preparing alkenes. But as we put a heading elimination, so let us go through this another type. What is alpha elimination? Alpha elimination is the term we use. I could say 1-1 elimination. What is that 1-1 elimination? When the two groups which I'm eliminating are present on the same carbon, then it is known as alpha elimination. When the two groups which we are eliminating are present on the same carbon. So let me give you one example. Now see this chloroform. On this chloroform, when I introduce strong base, you can have any base, alcoholic KOH you can use, you can have concentrated KOH aqueous, you can use PHLI and different types. But anyways, if you are using some base, then this H will behave acidic. Okay, so I will remove this H. Negative charge will come on this carbon, followed by this H plus loss, I'll lose Cl minus. So overall I can say this base has eliminated HCl from chloroform. But if you see the relative position of H and Cl, they are present on the same carbon. So I will say that the two groups which are eliminated are on the same carbon. It is a 1-1 elimination or alpha elimination. There could be so many examples of this also, but this one I find to be the most relevant, as there are certain name reactions which you need to in while studying those, which you need to know this type of elimination. I'm talking about trimer. I'm talking about cyclopropane formation from alkenes. At that time we'll be studying this in a slight more detail. Okay, gamma elimination. By far, you might have been uh, getting a clue that how these names are assigned. So, when the two groups which we are eliminating are placed alpha, beta, gamma to each other, then it is called gamma elimination. And the products formed by this reaction are cyclopropane. I can say anything after beta elimination, anything at a distance farther away from beta position, say gamma, delta, or any further position, it will lead to cyclization. It will lead to formation of cycloalkanes. And the smallest possible case is the formation of cyclopropane. Correct. Let me exemplify. In I think yesterday or day before yesterday, somewhere we studied the Woods reaction, and I told you the very high yield in this cyclopropane formation, almost 93 to 96 percentage yield is obtained. This type of dehalogenation with the help of metal is certainly an example of gamma elimination. So, this was the classification of elimination based on the relative positions of the groups that we are eliminating. Type B, that is the classification category B. This classification is based on the mechanism involved during elimination. What type of mechanism is functioning, is being operated during the elimination, on that particular criteria, the elimination is divided into four categories. Four categories I have written here already. Let me go through them. E1 reaction. E1 reaction, its name is unimolecular elimination reaction. Unimolecular elimination reaction. Now, this is a very standard IUPAC method of representing the mechanisms. Whatever thing we are writing here as a subscript, particularly in these three numeral subscript that we are writing, it represents the molecularity of the reaction. If I say E1, it is unimolecular. If I'll say E2, this one is certainly going to be bimolecular elimination reaction. Elimination reaction. So this down thing is molecularity. This capital letter we are writing represents what is being operated. Like E, if I am writing, I want to denote elimination. If I would have written S, I would have wanted you to interpret that it is a substitution. If I'll write A, I want you to interpret it as addition. Okay, so this subscript here, uh, not exactly subscript, but the downside return thing is the molecularity of the reaction. Okay, and E stands for elimination. So E1 is unimolecular elimination, E2 is bimolecular elimination, EI or EC is cyclic or intramolecular elimination. C stands for cyclic, or I stands for intramolecular elimination reaction. Elimination reactions. E1CB, it is again unimolecular. Unimolecular. Okay, unimolecular elimination through conjugate base. Don't get scared by these big names. They are easy to understand. We will go through it slowly. So just wait. So these are the four methods. Now, how are they classified? What is being done? Okay, let us understand those things. Okay, how are they classified and how it is being done? What am I saying? So we this whole thing. One thing I forgot to add here is this whole mechanistic approach or mechanistic classification is certainly of beta elimination we are doing. Now we are concentrating as per our requirement to prepare alkenes. So we are going for beta elimination classification, which is E1, E2, EI, and even CB. Now, what it is and why it is classified like this, let us do that. Let us assume a reactant in general has no idea what the mechanism is. The currency in chemistry or in nature is only thermodynamics, is only energy. It has nothing to do with that I am predicting it to be E1 or E2 or EI or even CB or what I know, what I like. It entirely based on thermodynamically which pathway has the least activation barrier under a given condition. So let us start and let us take an example in your mind. Whenever I'm saying something, please take alkyl halide as a general example. This L is the leaving group. If you don't want to take the word alkyl halide, take RL. L to be the leaving group, which in technical term is called nucleofuge. Okay, the leaving group is in technical term is referred as nucleofuge. So let us take that I have a alkyl halide, say like this. I want to remove this H index. Now, a molecule can have two pathways. Depending on the conditions where it is placed, it can form a complete carbocation, though we have done before that it is not that easy as it is on writing on a paper that I just broke a bond, wrote an ions and cation. No, no. It is a very gradual, step by step process which has a very important contribution by the solvent. Solvent decides how this will break, at what rate it will break, whether it will break or not. Okay. Other thing, it does not dissociate like this, and some base starts attracting, say this, H, beta H, and there is no formation of intermediate or something, a single step to alkene or dehydrohalogenation is done. Whereas here, once carbocation is formed, now it will lose, assuming similar, I'm taking this and leaving this at this point of time, that as a second step, it releases H and form alkene. Where this H goes, who takes it, there are so many variable things, but here I'm having a support of this X minus. Okay, so see, this is a two-step process. This is a single-step process. Okay, there could be other methods also. Other methods also, like this H leaves first, a complete anion is formed, H leave as H plus, and then X is gone. That is even CB. So what all I have written here, this track is representing E1, this track is representing E2, and for E1 CB, I'm moving here that if, now that is a reversible track, CH3, CH minus CH X CH3, and then there is loss of this X. So CH3, CH double one, CH, CH3. On a net, you will see that yes, elimination has been achieved by all the three methods, but the pathway is different. In one, carbocation is formed, in another, carbanion is formed. Whereas in this mechanism, no free possible intermediate is observed. It proceeded in a single step, and that is through transition state. So let us go one by one to each of them. First, E1 reactions. As we have already said, that it is unimolecular elimination reaction. Let me take a proper example to write the net reaction. Say this, it loses X, it forms carbocation, then this carbocation loses beta H, and we will have double bond. Out of these two, this step 1 is acting as RDS. This step 2 may decide the yield but will not control the rate. As in a multi-step reaction, we know that the rate is controlled by the RDS. So I can write the rate equation for this reaction is rate constant into concentration of Me3CX, or any substrate that you take in a given reaction condition and is showing even reaction. Now see here, when H plus, definitely there must have been some reagent which is supporting removal of this H plus, but it is not part of our rate equation. Okay, if you know there is something called substitution, once a positive is formed, anything that could act as a nucleophile that could attack on this plus charge will definitely compete here, and you will have a major byproduct like this. Even the normal bases, which are OH minus or NH2 minus or ammonia, whichever you take, they all are good nucleophiles also. So, E1 is always competing with SN1. It is a never ending competition. If you create a condition for E1, parallelly SN1 will come into scene. Now, which one will dominate? Now, we have seen that yes, there is a possibility of nucleophilic substitution, there is a possibility of elimination, and to make our things worse, both have the same RDS, both have the carbocation formation as RDS. So as far as the rate of the reaction is concerned, rate of a particular substrate in a given condition for SN1 as well as E1 will always be same. Now, if I want to prepare alkene, I need to suppress SN1. Otherwise, I lose my yield. I lose my yield to nucleophilic substitution products. Now, how can I suppress nucleophilic substitution, which otherwise seems to be thermodynamically very favorable? Why favorable? Why favorable? Because opposite charges can easily attack. Opposite charges are forming a sigma bond. So definitely it is going to be a less barrier reaction as compared to our elimination, where we are removing one more sigma, we are losing H plus and then forming pi. Okay, so how will I support this? I will use something which could act as a base but will act as a poor nucleophile. That is my one way to support elimination. Second thing, as and as the stability of this alkene formed will increase, automatically the barrier will go slightly down and down and down, and the reaction will shift relatively towards elimination. Third, the most important point is high temperature. What do I mean by high temperature? See, when you say elimination, even when we were writing a general reaction, a molecule, if there is a reagent, something that is causing, let me write it just a reagent, is definitely reagent is as such and AB. So I can say a minimum change that is possible in a normal elimination is a splitting of a molecule. 1 will go to 2, 2 is going to 3. So as and as this reaction is happening, this reaction is taking place, the number of particles on the product side are greater than the number of particles on the reactant side. If number of particles on the product side are greater, then I can say delta S for elimination is positive. Or if you don't want to use the term positive so affirmatively, you can say that the delta S for elimination is always going to be greater than the delta S for substitution. Okay, if delta S is greater, or I can say positive, then how will I use it to conclude the high temperature thing? Delta G is equal to delta H minus T delta S. Now for a reaction of elimination, I am breaking sigmas and we are correspondingly forming this pi. Okay, so this is also endo. This is also an endothermic quantity. This is also going to be positive. Now to make this delta G negative, with delta H being positive, with delta S being positive, I have only one thing in my hand, that is temperature. If I want the elimination to make spontaneous or to increase its yield and feasibility, I am left only with this temperature. Okay, the only key I have to unlock elimination lock is temperature. As and as I'll increase this temperature, this delta G will become negative, and thereby I can have that elimination reactions will become dominating or feasible. And this is why this was our point, that high temperatures are required for elimination to happen. Okay, we need higher temperatures for elimination to take place. So this was our general mechanism. This is our rate equation. This was the condition that we need high temperature. Point number 3, as in the RDS, rate determining step, a group is leaving. So with increase in leaving group nature of X or L, whatever you have considered, X or L, rate of even. Please have a very clear difference in your mind related to the word rate and yield. Something can be faster but may not give a very good yield. Something can be extremely slow but will give you a very good yield of a reaction. Currently, in this point number 3, I am bothered only about the rate. Okay, so as and as the leaving group nature of X or L increases, rate of even will increase. Okay, and the leaving group nature is inversely proportional to the basic strength, basicity, not the physical wala basicity that the number of um, H plus this base will accept. No, not that. The strength, basic strength, basicity of leaving group. As and as it becomes poorer and poorer base, it becomes better and better leaving group. Is it okay? Next, as again in the RDS, there was a formation of carbocation. So I can say that with increase in stability of carbocation, rate of even reaction will increase. As and as it will become stable and stable, rate of even reaction will increase. Okay, and for that, let me write a 3-degree RL will be having a faster rate of E1 as compared to 2-degree RL as compared to 1-degree RL. Correct? Point number 5. Point number 5 is regio selectivity of E1 reaction. Now, what is regio selectivity? From the word itself, regio, region, selectivity, selection. Region का selection, position का selection. Please pay attention that if in a particular even reaction, there is a possibility of formation of two positional isomers. Okay, if there is a possibility of formation of two positional isomers, and out of those two positional isomers, reaction creates or generates any one particular isomer in dominance, or if exclusively, either exclusively or in dominance, then we'll say reaction is selective about a particular regioisomer, positional isomer, and the reaction is said to be regioselective. This could be in any particular chemical reaction wherever there is a possibility of formation of positional isomers. Okay, it could be for anyone. Now, again, coming back to eliminations, here I have two possibility. I can have one butene I can have 2 butene in this particular example. And we found that this more substituted alkene, which is more stable by hyperconjugation, is formed or is created in a major or as exclusive percentage. So this reaction is regioselective. Okay, this is obtained as major. This we can never say that this is not obtained at all. And chemistry always talk in terms of major, minor, never talk exclusive. That is a very tough word to use, as all of those who know chemistry can understand. You can never say exclusive because the molecules are relatives to no one. Where they will go in what, I already told, the only thing they'll follow is thermodynamics. Okay, so they can take any turn at any point of time based on the thermo of that particular condition, that particular reaction. So, coming back here, this regioselectivity is framed by two laws: Z-save, Z-save's reaction, or Z-save's elimination. Now, there are different spellings which you may come across. Just don't pay any heed to what way or what this spelling is there. It could be Z-safe or it could be Z-safe's elimination also. Okay. Now, what does it say? It says formation of more substituted alkenes. What is Z-safe elimination? So you will say formation of more substituted alkene is Z-safe elimination. Formation of less substituted alkene we'll see later, just 2 minutes ahead. Okay. So I can say that this rule states that the double bond goes mainly towards the most substituted carbon. Then it is set safe. Okay. Of course, this rule may have certain exception conditions, but this is general major. Next is Hofmann's elimination. In Hofmann's elimination, it is just opposite of this. Here I will say the double bond goes to mainly least substituted carbon. In elimination, I can say, in E1, I can say ZZIF products are major products and major products. Okay. Next point, let us see where were we. Let's first go to that. We had point number 4 and Regio Selectivity is point number 5. Can even reaction be stereospecific and stereoselective? Stereospecific and stereoselective. Well, yes, it can be. I cannot deny that the even reactions are always non-stereospecific. Okay, they can be stereospecific. There is a strong possibility. There have been evidences which support that even reactions, even even, and even reactions are stereoselective and stereospecific. Sometimes condition defined, not always. Okay, that depends. Now, my term is not very valid for always. Like as I said, na ki sometimes. Now, if this and I take its even reaction, No point of discussion because there is formation of only one alkene. There is no other. The word selective will come only into scene when there is a possibility of more than one type of products and the reaction shows dominance or liking towards one. If there is no such thing, there is no point of having this word. See, if I have this, now again I would say no point. This is only one alkene. Okay. Then there was a choice of regio isomers that we have done. That yes, we may have a, different possible positional isomers, and then it shows some regio selectivity. Coming to stereo selectivity, see this one. If I dehydrate this, certainly by regio choice, this is going to be my major product. CH2, CH1, CH2 is very less minor. This is going to be major. But amongst this, there are two possibilities, na? Why? Because this molecule can have this, that is the E isomer of alkene and the Z isomer of alkene. Z isomer, E isomer. Okay, the E and Z isomers. Amongst these two, it is fine that, please make it a note in your brain, this one is almost 95% that we obtain. This is hardly 5%. So see, region wise they are both same, but a one particular stereoisomer is obtained almost exclusive. 95% is almost exclusive. Okay, so this type of stereo selectivity is certainly observed. But as I said, I cannot say it is always because in the above examples I've shown, if there is no stereoisomer possible, how can I comment? Is it okay? Now, definitely when I have this, there is certain stereo specificity on the pathway. So it may show all this behavior. Okay. Then we are moving to uh, next point, number 6, that polar solvents, polar solvents increase rate of E1. I think all of you will support that because RDS is carbocation formation. Okay, so that is okay. Next is, can it show isotope effect? Isotope effect. Well, practically, I would say yes. It can show a weak, not that dominating, but weak isotope effect. What I want to say, that dehydration of this, okay, dehydration of this alcohol will definitely be faster than this. If I want to talk about the rate, this is what the rate of dehydration dehydration of this reaction will be. And the reason is the presence of alpha H and presence of alpha D. As it comes to D, certainly there will be higher barrier for the elimination. So yes, it is showing, but it is not showing the primary kinetic isotope effect. Okay, isotope effect, but poor. Okay, but poor, not to the level that is shown if this H comes. This its numerical values are hardly, I don't have the exact data in my hand at this point of time, but they are not like the primary ki effect with 7 or 5 or 12 or higher range side. It is not so in here. So for J, do not go much to this isotope effect use. Okay, so because it is less. Then, as it involves carbocation, of course, overall conditions we have discussed. Anything that supports formation of carbocation will support elimination E1 mechanism. I want to use a rough energy diagram also to represent my points. That is my last point for E1. If I could use, okay, this is the growth of the reaction. Here I'm using the free energy change. I'm starting with reactant, dehydration of alcohol, or not dehydration of alcohol, any even reaction. Okay, a carbocation is formed, and then carbocation eliminates and an alkene is formed. Okay, this is alkene, this is R plus, this is RL. Okay, as you can see, the barrier for this step is high. So this is our RDS. This step will act as our RDS. Okay, if you have two alkenes, definitely you can have two graphs, 2 points here. Correct? Moving to any example of E1, there are not many because SN1 takes away the whole, what should I, thunder of the reaction. Okay, SN1 becomes so dominating. So there are not many, but yes, we can have some. And for that, we have one, that is dehydration of alcohols. Dehydration of alcohols. Let me write certain CH3, OH, CH2, CH3, general mechanism. We use strong acids like H2SO4, H3PO4 to protonate. This is our first step. CH3, CH3, OH2 plus, CH2, CH3 plus, HSO4 minus. So protonated alcohol is formed. Now this protonated alcohol will release water. So water is gone and we'll have carbocation. Here there is no rearrangement, but if there is any possibility of rearrangement, as we have a free carbocation, so if there is any possibility of formation uh, of rearrangement of carbocation, certainly it will be observed. Okay, there will always be a possibility that rearranged products will be obtained in SN1 reaction. Rearrangement of C plus is observed wherever possible. So there is a possibility. Abhi nahi hai because already it is a 3-degree carbocation. Now it may lose with the help of HSO4 minus either side, and the other possibility is this. This is certainly major, this is minor. Now see how many steps. 1, 2, 3. Here we came across that it is a 3-step reaction. Okay, so for this, if I draw an energy diagram, I'll say alcohol. This is my ROH2 plus protonated alcohol. It will be down. Same way, energy reaction. Now this will form carbocation. If there is rearrangement, one more thing will be added. Now this is forming two different, let me have a better this. Now it is forming two different alkenes. Say one alkene and another alkene. Okay, like this. A barrier for one is different than another. Yes, that is possibility. When I draw from the same, then I want to say geometrical isomers. When I'm having these different slopes, I'm talking about regio isomers. So this is more stable. This will represent Zef alkene. This will represent Hofmann alkene. This is representing carbocation. Okay. RDS is formation of carbocations, so same factors will be observed if it is even. Can elimination of alcohols be E2, or the one that we are going to study? Yes, it can be. Okay. Usually dehydration is even. Dehydration is even. Okay. I can say particularly for 2 degree and 3 degree alcohols, it is even. For 1 degree, I will not call it even. It has its different pathway. We'll study. Just give us some time. So here if you see, it is a completely reversible reaction. The reverse reaction is addition of water under acidic condition to alkenes and formation of alcohols. Formation is removal of water and formation of alkenes from alcohols. Okay. So net reaction is certainly can be written as CH3 CHOH CH3 CH2 CH3. We said that we need H2SO4. We are forming major alkene and water. Okay. H2SO4 remaining as such. So water is in the product side. So this should be concentrated H2SO4. If you want to add alkene per water, you need a dilute H2SO4. Purpose or reason, Le-Chatelier reaction, Le-Chatelier conditions. Okay, following the Le-Chatelier, we are having this particular whole thing that um, how will all of this will work. Okay, is that clear? We can use only concentrated H2SO4 or H3PO4. If you want to go for some catalytic support, the maximum we have is Al2O3. This all will give you ZZIF product as major. This all will give you ZZIF product is as major products. Okay, why can't we use other acids in place of this? What are my choices? If I go for other acids which are oxidizing like HNO3 or HClO4, no, big no, because they will oxidize our alcohol to acids, which is not what we were wanting or we were trying. If I used HX, then the conjugate X minus is nucleophilic, and will give SN products as major products. So I am not at liberty that I can use any which way acid I feel for. No, I have a limited choice. Okay. Now, in a general even, I told that as and as the stability of alkene increases, the percentage of elimination or the ease of elimination increases. Correct? As and as the stability of the alkene increases, the ease with which we can have the elimination increases. Just to exemplify my point, I would like to add here that yes, if I can say um, for 3 degree alcohols and I want to do dehydration using this whole method that we were just discussing, give me a second. Let me write what I'm saying. So if I have MEC, ME, MEOH, and now I want to dehydrate it, the condition that I need is, just see, you will be amused, 20% H2SO4 and 85 to 90 per degree centigrade. You will have isobutylene as a good yield product. Okay, no problem. If I take a say 2 degree alcohol, then I need 60% strength of H2SO4 and 100 degrees centigrade is the temperature. Then I will have butene. If I take 1 degree alcohol, Then I need 75% H2SO4. See, strength of the reagent is increased and temperature is 140 degrees centigrade. To get, still the rearrangements will be there and I'll get the 2-butene as a major product. If I take ethanol, the alkene is totally non-hyperconjugative. I need 95% H2SO4 and temperature has to be around 170 degrees centigrade. Then I can produce ethene. Okay, this clearly indicates that how the stability of alkene is deciding the reaction. So as and as the alkene is becoming more and more stable, I can get alkene as a major product under less vigorous conditions. Along with alkene, there is certainly a possibility of ether as a byproduct. Ether byproduct. But as and as the stability of alkene is increased, the byproduct ether automatically goes on a little down and down, decreased and decreased. Is that okay? So this is how general dehydration can work in case of alcohols. Now I have really skipped till now about the 1 degree alcohols, how they could have given us this type of rearranged products. Okay, so let me just, as it is a phase 2, I expect some of you still remember butane 1 all. So when I take H plus, I'm just going to use the term E2 here, OH2 plus. Now this goes E2 and CH2, CH1, CH2 is formed. Now again as it is H2 and H2SO4, formation of, and then this by E1 form trans to butene. Okay, so there is a strong possibility that it could have been E2, then addition, and then again elimination. That is why 1 degree alcohols still give more substituted alkenes. Okay, I hope it is quite clear to you that how for alcohols this whole thing has worked out. Right? If rearrangement are there, yes, we have to take rearrangements, no choice. Now, besides this, are there any more examples of even reaction? Well, I would say not many. Yeah, during solvolysis reaction, solvolysis reactions, if temperatures are maintained high, then even can be obtained. That is a possibility that is there, but can't be like a very important reaction. Moving to next examples or next category will be certainly E2 reactions. But as E2 reactions are extremely important and by themselves a very important class and number of examples to be covered, I'll like to postpone it to my next lecture. Okay, because I would not be able to complete it in a one go today. I'll take E2 and even CB in a coming lecture. Right? So, till then, you revise your notes, and tomorrow we'll solely concentrate on what is E2 reaction. Please join me tomorrow compulsorily as E2 reactions are extremely important. And the most important confusion is the elimination versus substitution. I'd like to have a slight discussion on that one also. Okay, till then, do take care and join me tomorrow again for bimolecular elimination.